Everyone. My name is Lucas Tonetto. So I'm here to present a bit about the work that I have been doing with my supervisor, Omar Benar, in Rome in the past few months. So essentially, I'm going to talk about thermal effects on nuclear matter properties, and I think we can see this talk as something complementary to the talks that have been done regarding the equation of state this week, because I'm going to be a bit more focused on the microphysical part of the equation of state. So this is the outlook of my presentation. So the very first topic that you talk about is why we should consider finite temperature equations of state in neutron star physics. And then I'm gonna jump to the part where I'm gonna talk a bit about the nuclear dynamics that we are using here in our model, and also how to generalize this model from zero temperature to finite temperature. Then I'm going to talk about some of the results going from the micro quantities, such as the single particle energies and let's say the Fermi distributions, the effective masses, and also I'm going to talk about the macro quantities, such as the free energy, internal energy, entropy, etc., and also symmetry energy and other related quantities. So the first thing that we should ask ourselves is why we should consider hot equations of state in neutron star physics. So one of the very strong motivations would be if we want to study merger and post-merger evolution, we should bear in mind that the temperature in these cases are far from zero, actually. Of course, it will depend on every point in space-time, but we have the temperature getting higher in this kind of systems. So we should have an equation of state that could satisfy the constraints coming from the zero temperature side, and also that could be thermodynamically consistent built in the finite temperature scenario. Also, if we want to study proton-neutron star evolution in supernova modeling, hot equations of state are necessary. And when we talk about finite temperature effects in neutron star matter, it's not just a matter of talking about the thermal contribution to the pressure and to the energy density. Of course, they are important because you should have a different, for example, if you want to talk about mass radius relation, you should have a different one. But also it's important to analyze, for example, neutrino reaction rates, because temperature plays a fundamental role there as well. So if we want to understand from the micro to the macro, we should bear in mind all the role that the temperature plays. So first of all, here I'm not gonna talk about relativistic mean field model. Actually, we work within the context of non-relativistic nuclear many-body theory. Some of the well-known equations of state, such as the APR equation of state, are based on that. So here, the basis of non-relativistic many-body theory is this Hamiltonian that you can see, where we have a kinetic part, a two-body potential, and a three-body potential. If you are curious about why we choose these phenomenological potentials here, for the nuclear potential, they are going to be V6 prime, and for the trinuclear potential, they're Bonan, I can answer your questions, of course. But the point would be that we have chosen these potentials because they, first point, they describe some of the constraints we have from bound states, from bound nuclei, and also from scattering data. So, and yeah, if you are curious about that, I can answer all your questions. So, but also we have this Hamiltonian, and the next question would be, how can we extract properties of this Hamiltonian? How can we compute, for example, the ground state energy of the system, the pressure, etc.? And there are different techniques to do that, actually. For example, the API equations of state use a technique called Fermi hyperneted chain, while here, actually, we use a different technique, which is basically, we call CBF effective interaction, which stands for correlated basis functions effective interaction. So the idea here is the following. So nuclear interactions, the nuclear-nuclear interaction is strongly repulsive at short distance. So we can't perform standard many-body perturbation theory. A way to overcome this problem in practical calculations is, for example, this one that we take, we renormalize the nuclear-nuclear potential in the coordinate space in such a way that we are able to perform these perturbative calculations in the Fermi gas basis. And the main point here is that in this effective potential that we build here, we are able not only to overcome this problem of the intrinsic non-perturbative behavior of nuclear-nuclear interactions, but also we are able to include the effects of trinicon forces in this two-body effective potential here. And I think those are the most important things that we can talk about this effective interaction here. So just to illustrate the impact, for example, if we compare the bare nuclear potential would be this black line here to the effective potential, we see that the bare nuclear potential is strongly repulsive at short distance, while in this effective interaction, of course, it would be still repulsive, but then it's not so repulsive such as, so we can perform a perturbative analysis of our system here. Now, so just to make you a comparison, the results that we get from this formula is actually the CBF effective interaction was developed in the 80s, in the 90s. And here we are just actually, we have an upgraded version where we can put together also the three nuclear forces here as well. And the results we get, they reproduce other kind of techniques, for example, the Fermi hypernetary chain technique used by the APR equation of state. But so, okay, we have our nuclear dynamics here, our nuclear Hamiltonian, but then there is the question. We have these nuclear dynamics at zero temperature. How we generalize to finite temperature? Again, we should do this in a thermodynamically consistent way, right? So, but the very first hypothesis that we assume here is that, okay, at finite temperature, but at a temperature not so high as the biomass, the nuclear dynamics, the nuclear Hamiltonian does not change. So essentially the Hamiltonian that we use at finite temperature is the same from that you use at zero temperature. And this is valid thinking about that in a neutron star merger, for example, temperature can be as high as 100 MeV, for example, but a typical temperature would be 50 MeV, 40 MeV, a typical high temperature. And so that's a fair hypothesis. So then where the temperature effects would enter in this system? So mainly if we think about a degenerate system of nucleons, we think about the Fermi distributions, because at zero temperature, we have a step function describing these Fermi distributions. Now, in the situation where we have this finite temperature, it's not a step function anymore. So the temperature effects would be included within the chemical potentials, the single particle energies, and of course, on the explicit dependence on the temperature. And it's important to say that if we try to perform perturbative calculations of nuclear matter in the finite temperature scenario, sometimes we do not reach thermodynamic consistency. So instead of performing perturbative calculations, here we choose a variational approach. So our idea is the following. We have a triogram canonical potential, and we minimize this triogram canonical potential with respect to the Fermi distribution. So that gives us the Fermi distribution, which would be essentially the most important building block of our system here at finite temperature. So that's the standard Fermi distribution that we know. And so as we can see, we have the temperature playing a role in the single particle energies, E of kappa T, also in the chemical potential, and also in the explicit independence in 1 over T, right? And the single particle energies, as well, as you can see, they are here. We have a kinetic part, we have an interaction part, and we have another part which is related to the density dependence of the potential here. So the main point here as well, everything that we do here must be thermodynamic consistent. So the Fermi distribution depends on the single particle energy and vice versa. So when we are trying to read this thermodynamic consistency, we need to solve the system in an iterative fashion, such that we can reach finally the thermodynamic consistency. And so now some of the results regarding the differences between the zero temperature scenario and the finite temperature scenario here. So let's start by the Fermi distributions. So as a baseline for our comparisons here, we are taking neutron, proton, electron, and muon, beta stable matter, right? And it's important to say that at finite temperature as well, neutrinos should play a role in the chemical potentials as well. In the calculations, in the comparisons that we show here, we are not taking the neutrinos into consideration. But this is just a baseline. Of course, we could add neutrinos as well if we wanted to talk about the neutrino influence here as well. But so here we have the family distributions for neutrons and protons at 2 times nuclear saturation density. And as you can see, okay, so the deviation with respect to the 0 temperature family distributions for neutrons is larger than if we compare for protons. And why so? If we are talking again about beta stable matter, the proton fraction is smaller than the neutron fraction. So, which means that actually neutrons are more degenerate than protons. So thermal effects in a more degenerate matter should play a less important role, right? And that's what is reflected in beta stable matter here. So for neutrons, we are always expecting that thermal effects would be less important than for protons. So in beta stable matter, it's important to have this different treatment for protons and neutrons. And it should be said that this arises naturally from all the thermodynamic consistent process that we develop to extract the nuclear properties here. And also, of course, we could work at arbitrary proton fraction, not only beta stable matter, but again, I'm taking beta stable matter as a baseline here. And after the family distributions, we can take a look at the single particle energies because they are the second most important building block of our system here because they are essentially containing the information about the energy of these single particles here in our system, right? So again, as I told you, for neutrons, the effects of temperature, for example, the deviations with respect to the 0 temperature case are much smaller than for protons. Again, this is related to the fact that neutrons are more degenerate than protons here. And also, I think that we have heard about in this week a bit about the effective masses. But why are the effective masses so important in these systems? So first of all, the effective mass is nothing, it's just a way to include all the interaction effects of your system in a, let's say, in an efficient way. Let's say, for example, the effective mass is defined as this expression that you can see in our situation. But the main point is that the thermodynamic, the interaction part of the thermodynamics of the system is contained within the single particle energies. The effective masses are like just a way to rewrite this contribution in a slightly different way that could be more interesting to perform phase-space calculations, for example, if you want to talk about neutrino reaction rates and other properties. And again, the effective masses as well, they depend on temperature. So if we talk about effective masses, we talk about a dependence on density and also dependence on temperature. And as you can see here, again, for protons, the impacts of temperature are larger than for neutrons because neutrons are more degenerate, right? So another important consequence of temperature, because when we talk about beta stable matter, we think about the 0 temperature scenario. But if we increase the temperature, when we try to reach beta stability, again, the proton fraction, the lepton fractions, they will not be the same because temperature does affect the chemical composition of the systems. So it's not just a problem of adding temperature to the case. For example, you add a thermal contribution to the pressure and to the energy density, but I also should understand how the chemical composition of this hot neutron star matter would behave as well. And I think the most prominent characteristic that you can see from the figure is that at the 0 temperature scenario, either for matter with only electrons and with electrons and muons, it's a monotone curve here. While at finite temperature, the proton fraction has a point of minimum and then it increases again. This is due to an interplay when we are computing the beta stability conditions, the quality of the chemical potentials. There is an interplay in the leading terms for the proton terms, the neutron terms, and the electron and muon terms. And so this point of minimum arises here. So I think that's the most important characteristic. So now that we have talked about these micro quantities, let's talk about some macro quantities. So let's first start from the free energy. The free energy is one of the most meaningful quantities that we can work with when we are trying to explore finite temperature quantities in our dense system here. And as you can see, the curves for the free energy here tend to converge at high densities. Okay, so if we think about, again, for more degenerate systems, thermal effects should play a less important role, right? So we would expect that actually at high densities, the curves would approach that from the zero temperature calculations as well. And for the plot of the free energy, it seems so, but I think this must be more evident if we look at the plot for the pressure, actually. So this is the pressure, again, for beta stable matter. And as we can see at high densities, all the pressures are essentially the same. So when talking about parameterizations that we can use to generalize thermal contributions, etc., we should bear in mind that the thermal contribution at low densities is different from the thermal contribution at high densities. So at high densities, all the pressures here tend essentially to the same curve, to the curve of zero temperature. And so this week, we have heard about also the symmetry energy here, right? So the importance of the slope of the symmetry energy and how the symmetry energy would behave. So the symmetry energy comes from microscopic calculations, as you can see. And again, there is a dependence on temperature, as you can see. And the very same feature that at high densities is dependence is weaker. But as we can see, there is I would say it's not possible to say slightly, but there is a nonlinear behavior of the symmetry energy here. Of course, around one-time nuclear saturation density, we could perform a Taylor expansion. Yeah.
Thank you. My question is very simple. How do you define the symmetry energy in this case?
It would be the difference between pure neutral matter and symmetric nuclear matter.
Okay, thank you very much.
And so, okay, that's the behavior of the symmetry energy of our system for both zero temperature and finite temperature scenarios. And as a matter of comparison, if you want to compare two values that have been mentioned, for example, the symmetry energy and the slope at the zero temperature scenario are those values there. So they are within, let's say, the experimental constraints that we have so far. Right. So, okay, that's the symmetry energy. And also, important thing to say about the symmetry energy would be that asymmetric nuclear matter is often parameterized in such a way that you can perform an expansion around symmetric matter, right? As we can see here. And in literature, there are some works that say this quadratic approximation works well at zero temperature, but does not work well at finite temperature. But apparently, for our case, of course, there is a deviation if we are working at high temperatures. But apparently, this quadratic approximation is a good approximation, even if we are working at finite temperature. At zero temperature, it's better. But at finite temperature, it's still, let's say, roughly speaking, it's still okay. And so just to finish my presentation, because I have been talking about microphysical calculations, exact calculations, but we know that in the neutron star market of equations of state, there is a lot of cold equations of state. But there are much fewer hot equations of state because this is a challenge generalizing the zero temperature scenario to the finite temperature scenario. So people have resorted in this, I would say, last 2 decades to parameterizations that could simulate these thermal contributions. One of the first parameterizations that was used was the so-called hybrid approximation, or essentially the approximation in which you add a thermal contribution to your pressure and energy density as an ideal fluid contribution, right? So you take the zero temperature equation of state and you add this ideal fluid term to your equation of state, and then you simulate these thermal effects. As a first step, of course, this is valid because, again, if we want to generalize the largest number of code equations of state that we have so far, it's a fair approximation. But again, this overestimates the contribution to the contribution of the thermal pressure at high densities, because as I told you, at high densities, the thermal effects are less important. So in 2019, a group of Reito et al., they have proposed a different parameterization. So instead of working with this ideal fluid parameterization for the whole density range, at intermediate densities, they consider, yes, this ideal fluid, but at high densities, they just consider a degenerate Fermi gas. So it's essentially a Sommerfeld expansion for a degenerate Fermi gas at finite temperature. And if we compare this, let's say, upgraded parameterization to our results. So here the solid lines represent our exact results for our macrophysical calculations, both for the internal energy and for the pressure, and the dashed lines would be the parameterization. As we can see, for example, for T equal 10 MeV, the parameterization works pretty well, right? And of course, if we increase the temperature, the parameterization is a bit worse, but it's still reasonable. And if we were to compare as well to the ideal fluid parameterization, where you just add this ideal fluid thermal contribution to the whole density range, the situation would be much worse. So I would say that from a nuclear point of view, if you work with simulations, and I think with neutron star merger simulations, I think it's interesting to use this updated parameterization because it takes into consideration these degeneracy effects at high densities. And so now I'm going to jump to the conclusions and the perspectives for the near future. So I think the most important take-home messages here would be, so robust finite temperature equations of states are fundamental to multi-messenger astrophysics, mainly if we are talking about having detections of post-merger gravitational wave radiation, the electromagnetic counterpart. If we want to understand more about processes involving neutrinos, etc., we need to have robust finite temperature formalism. So thermal effects in this scenario, as well as I told you in beta stable matter, they are more important to protons than to neutrons. So you can't give the same treatment that you give to protons to neutrons. And also temperature also affects the chemical composition of neutron star matter. So again, when we go from T equals 0 to T equal 10, 30, 50 MeV, chemical composition of beta stable matter changes. And if we want, again, to study phenomena such every phenomena involving neutrino reaction rates, for example, bulk viscosity, we should bear in mind that these single particle energies and effective masses depend not only on the density, but also depend on the temperature. And finally, something that I have been doing now, I'm applying these calculations I'm trying to compute bulk viscosity of this hot neutron star matter. So thank you.